Managing async boundaries is about creating a wall between your application logic and the unpredictable nature of external data. So, you're basically managing the state inside your application and the possible side effects of your data. If you treat an async call as a single messy event, you end up with race conditions and UI glitches. To do this deeply, you must treat the sync boundary as a three-play act: the setup, the flight, and the landing. First, the anatomy of the boundary: phase before call, React equivalent, render phase. The rule: capture current state or intent, set loading to true, phase mid-flight, React equivalent, the void. The rule: zero state mutation. The app should be read only regarding this specific task. So just like with atomicity and concurrency concept, the middle part or the execution part are always read only, so that you can only have two possible states, before or after. After call, commits phase, resync with reality, apply the result, and clear loading. Second rule: never mix state mutation mid-flight. In React, render must be pure. In async, flight must be pure. If you mutate state during an await, you create stale closures. So, like if you change this using this await that we see in code at the middle, you basically create a stale closures in which that hasn't complete yet, but you basically mutate it, so the UI might reflect a world that no longer exists by the time the promise resolve. The clean pattern for JavaScript: const argument status comma set status equal use state argument idle, and then async function handle update argument new data, and then inside it boundary start the pre-commit set status argument loading semicolon next line, const capture id equal current id semicolon or closing, which means capture the context, then try the flight, no state mutation allowed here, const response equal await API that save argument new data, and then semicolon, and then next line boundary end post no conflict, if capture id equal current id open semi-curly bracket. So this means check if we are still on the same page. Next line set data argument response semicolon, next line set status argument success semicolon closing semi-curly bracket, and then catch argument error open semi-curly bracket set status error closing. Third, managing the stale state problem. The biggest danger of async boundaries is that the user might do something while the promise is pending. If you don't define the boundary, you get ghost updates. An old request finishes and overrides new data. So while the promise is pending, it means while it's in mid-flight. So if you don't define that boundary in await, you get the ghost updates or stale closure. An old request finishes and overrides new data. How to enforce the boundary? First, abort controllers. Think of this as canceling the commit. If the component unmounts or the ID changes, kill the flight. Second, versioning. Give every async request a version ID. When the promise returns, if the version ID in your state is newer, discard the result. Third, local variables. Only use variables captured before the await to decide what to do after the await. So this is common sense, but still helpful to be reminded to only use variables that has been captured before the await. Fourth, conceptual alignment with React. You mentioned the separation of state change to render to side effect. Here is how that maps to a sync boundary. First, intent action. User clicks save. Second, transition before you update UI to saving. This is like React's render phase. You're projecting the future. Third, the work async. The network call happens in the background. This is the scheduling. Fourth, the reconciliation. After the data returns, you compare it to the current UI state. If it's still relevant, you commit it to the screen. Crucial insight, an async boundary is essentially a manual reconciliation steps. Since the real world, the API is not managed by React's virtual DOM. So since the third party or the services from the server are not managed by virtual DOM, it's actually preparing you to handle those external data by managing your state or preparing your component to be able to respond to that no matter what. You're responsible for deeping the API result against the user's current context before updating the state. It's a classic chicken or egg dilemma in learning patterns. But if you want to become proficient developer quickly, the answer is almost always pattern first, syntax second. Think of it like learning a spoken language. Syntax is the grammar and spelling, while patterns are the ability to hold a conversation. You can memorize a dictionary, syntax, but you won't be able to tell a story, patterns, without understanding how thoughts are structured. First, why patterns are the priority. Patterns represent logic and problem solving. Most modern programming languages are actually very similar in their DNA. Once you understand the pattern, switching language becomes a simple translation exercise. Logic is universal. A for loop pattern exists in almost every language. Whether it uses curly braces or indentation doesn't change the logic of repeating an action. Preventing the tutorial hell. If you only learn syntax, you'll find yourself looking at a blank screen wondering, I know what an if statement is, but I don't know how to build a login system. Architecture, patterns teach you how to organize code so it doesn't break when you add new features. Second, the role of syntax. Syntax is the technical requirement to make the code run. It's the barrier to entry for the computer to understand you. Syntax is Google able. You can always look up how to declare an array in Python. It's much harder to Google how do I structure a scalable payment processing system without knowing patterns. The compiler is your teacher. If your syntax is wrong, the computer will give you an error message immediately. If your logic pattern is wrong, the computer might run the code perfectly but give you the wrong result, which is much harder to fix. Comparisons at glance, feature, focus, syntax the how, commas, brackets, keyword, pattern the why, logic flow, data structure, design, feature transferability, syntax the how, low, changes between language, pattern the why, high, applies to almost all languages. Feature learning method, syntax the how, memorization and repetition, pattern the why, critical thinking and project building. Feature analogy, syntax the how, learning how to hold a hammer, pattern the why, learning how to build a house. The best of both worlds approach, you shouldn't learn them in total isolation. The most effective way to learn is pattern-driven syntax. First, identify a goal. I want to check if a user is old enough to enter this site. Pattern conditional logic. Second, learn the syntax. Look up how to write an if-else statement in your chosen language. Third, implement, write the code. Fourth, abstract. Notice that this same logic applies to is the password correct or is the item in stock. Pro tip, don't stress about memorizing syntax. Professional senior developers look up basic syntax every single day. They are paid for their mastery of patterns. These two books represents the mastery stage of the pattern over syntax philosophy. The Ousterhout and Osmani design patterns. If the basic patterns like loops and if statements are the sentences of programming, their book are teaching you how to write novels and epic poems. Here is how they specifically relate to the points we discussed. First, moving from micro patterns to architectural patterns. In our previous discussion, we defined the patterns as basic logic, like a for loop. These books take that a step further. Adi Osmani teaches design patterns. These are high-level structure patterns. For example, instead of just learning how to write a function syntax, it teaches the observer pattern, a way to make different parts of your app talk to each other without being tangled together. John Ousterhout teaches philosophy or principles. He focuses on the pattern of information hiding. This isn't a line of code you can copy. It's a mental pattern of how much should this piece of code know about that piece. Second, solving architecture, point 1 in your list. Your list mentioned that pattern teaches you how to organize code so it doesn't break. These books are the gold standard for that specific goal. Osmani's book prevents spaghetti code by using established patterns. You aren't guessing how to build a system. You're using blueprints that have worked for 30 years. Astor Howard's book, Tackle Complexity. He argues that the greatest pattern of all is making modules deep, simple interface, powerful internal logic. This relates directly to your point that syntax is easy to Google, but architecture is what makes a developer valuable. Third, syntax as the backseat driver. Both authors treat syntax exactly how we describe it, as a secondary tool. In Osmani's book, you will see a lot of JavaScript code. However, if you ported his singleton pattern to Python or Java, the logic remains identical. The syntax is just the ink used to write the story. In Ousterhower's book, he often criticizes certain ways people use syntax, like overusing exceptions. He views syntax as something that can actually get in the way of a good pattern if you aren't careful. Fourth, avoiding tutorial hell. You mentioned that syntax only learners get stuck at a blank screen. These books are the antidote to that blank screen. They provide the mental models needed to look at a complex problem like building a text editor or a shopping cart and see the invisible structure before you even type a single bracket. Summary of relationship, concept from your list. Logic is universal. How Osmani and Ousterhower apply it. They prove that clean code is a universal language, whether in JS, Java, or C++. Concept from the list. Syntax is Google label. How it applies. They assume you can look up how a class works so they can spend time teaching you why to use one. Concept from the list. Building house. How it applies. If syntax is the hammer, Osmani provides the blueprint and Ousterhower provides the engineering physics. If you follow the patterns before syntax rule for a single language, adding these foundational subjects like OS, DSA, etc. is like learning the law of physics before you try to build a skyscraper. Here's how those subjects provide the deep logic behind the patterns you find in books like Osmani's or Ousterhout's. First, why these foundations matter for patterns. You can learn a pattern, the what, without these foundations, but you won't understand the trade-offs, the why. DSA, data structures and algorithm. This is the DNA of patterns. You can't understand why a database uses a specific pattern without understanding B-trees or hash maps. DSA tells you if your pattern will be fast or slow. So you won't be able to understand why the database that you're using behave like that if you don't understand the B-tree and hash map data structure. DSA allows you to tell the time complexity of that. OS and CPU structure. Teaches you how memory and threads work. If you learn the singleton pattern but don't understand concurrency or CPU caches, you might write a pattern that actually crashes your program or runs slowly on modern hardware. So you may misapply that pattern because you don't actually understand how caching works. For example, like a client rendering and server-side rendering, you might think that based on theory, client-side rendering is more slow, but because of cache and how fast our hardware today, they actually looks almost the same in practice if you only have a small users. Database, this teaches you the pattern of persistence. It helps you understand why we separate data from logic, a core theme in almost every design pattern book. Another thing is that this is also how you would see with CPU architecture. Data and logic is separate, the code, and even with OS and with the full stack application, you basically separate your logic, the code, and the data which inside your database. Networks, this explain the latency pattern. It's why we use patterns like asynchronous programming or proxies. So for networks, that's more of like it's the same with React, using await to handle those outside surveys. So you use this asynchronous programming to be able to wait for them to respond, such as database. You do network calls to a database or etc. Second, the risk of learning everything first. Well, these are important. There is a major trap: analysis paralysis. If you try to master CPU architecture, OS internals, and networking before you write your first code, it may, instead of learning them all before syntax, think of it as a virtuous cycle. Most successful engineers learn in this order. First, surface patterns and basic syntax. Learn enough to build something small. How do I make a list of names? So I think that's a great start, because you would see the fruits of your labor. So another thing is that to look at the work of your colleagues or the people you want to be. It will really accelerate your motivation. Second, DSA, the foundation. Once you code a bit, learn data structures, this immediately makes your patterns more efficient. Third, advanced patterns, Asmani or Asterhout. Now that you have the logic, learn how to organize big systems. Fourth, low-level foundations, OS/CPU/networks. As you encounter complex bugs like memory leaks or slow network requests, dive into these subjects to understand the under-the-hood mechanics. So the OS and CPU and networks are actually at the end. So how do you relate to your two books? Subject, OS or CPU? Relation helps to design patterns, help you understand complexity. If you know how the OS manages resources, Asterhout's advice on deep modules makes more sense. DSA, Asterhout argues for clean interfaces. DSA provides the efficient guts inside those interfaces. So DSA is kind of like the implementation, the data structure and algorithm in the implementation and interface separation. Networks, essential for understanding distributed system, which is where software design becomes most difficult. The verdict: is it important? Yes, but not as a prerequisite. Think of syntax as the tools, pattern as the blueprint, and the foundation, OS, DSA, the CPU, the database, as the science of materials, knowing how much weight the wood can hold. If you only know syntax, you are a hobbyist. If you know syntax plus patterns, you are a professional. If you know syntax plus patterns plus foundations, you are an architect.